Good day, everyone. I am Christine May A. Merculita from BSED Math 1A, and I'm going to report the topic about resolution in astronomy during 17th century. The 17th century is the period of the scientific revolution witnessed the consolidation of Copernican heliocentric astronomy and the establishment of inertial physics in the work of Johannes Kepler, Galileo, René Descartes, and Isaac Newton. This period was also one of the intense activity and innovation in mathematics, advances in numerical calculation, the development of symbolic algebra and analytic geometry, and the invention of the differential and integral calculus resulted in a major expansion of the subject areas of mathematics. However, we can't be able to discuss this one by one. We can only focus on the resolution in astronomy and what are the most important discoveries during that time that can add up more information in the field of mathematics. Moreover, astronomy has always had a significant impact on our worldview. Early cultures identified celestial objects with the god and took their movements across the sky as prophecies of what was to come. We would now call this astrology. Far removed from the hard facts and expensive instruments of today's astronomy, but there are still hints of this history in modern astronomy. Take for example, the names of the constellations Andromeda, the chain maiden of Greek mythology, or Perseus, the demigod who saved her. Let's move on to the top 10 most important discoveries during this time. The first one is the extrasolar planets. Extrasolar planet, also called exoplanet, any planetary body that is outside the solar system and that usually orbits a star other than the sun. Extrasolar planets were first discovered in 1992. More than 5,000 are known and almost 9,000 await further confirmation. The discovery. An extrasolar planet is one that's outside of our solar system, and astronomers believed in their existence for a long time. Yet, it wasn't until recently that the tools to actually spot one became available. It was only in 1995 when Swiss astronomers Didier Queloz and Michael Mayor discovered a planet in the constellation Pegasus dubbed 51 Pegasi b. Yeah, astronomers may be great at discovering things, but they are not great at naming them. An extrasolar planet, also known as exoplanet, is a planet that orbits a star other than our own. Our solar system is only one among billions, and many of them most likely have their own system of planets. As early as the 16th century, there have been astronomers who hypothesized the existence of extrasolar planets. Number 2 is the cosmic microwave background radiation. The cosmic microwave background, or CMB, is the cold remnant of the first light that could ever travel freely throughout the universe. This fossil radiation, the farthest that any telescope can see, was released soon after the Big Bang. Scientists consider it as an echo or shock wave of the Big Bang. Over time, this primeval light has cooled and weakened considerably. Nowadays, we detect it in the microwave domain. ESA's Planck mission will detect this first light, which is also the oldest radiation detectable and carries information about our past and future. By observing it, Planck will be seeing the universe as it was almost as at its origin. The discovery. It was a pair of radio astronomers, Arno Penzias and Robert Wilson, who discovered cosmic microwave background radiation in 1964. CMBR is a type of radiation that's present in very small quantities, hence the term background, all throughout space, and is believed to be left over from when the universe was in a very early stage of growth. The third one is the radio astronomy. Radio astronomy is a subfield of astronomy that studies celestial objects of radio frequencies. The first detection of radio waves from an astronomical object was in 1933, when Karl Jansky at Bell Telephone Laboratories reported radiation coming from the Milky Way. Subsequent observations have identified a number of different sources of radio emission. These include stars and galaxies, as well as entirely new classes of objects, such as radio galaxies, quasars, pulsars, and masers. The discovery of the cosmic microwave background radiation, regarded as evidence for the Big Bang theory, was made through radio astronomy. Radio astronomy is conducted using large radio antennas referred to as radio telescopes that are either used singularly or with multiple linked telescopes utilizing the techniques of radio interferometry and aperture synthesis. The use of the interferometry allows radio astronomy to achieve high angular resolution, as the resolving power of an interferometer is set by the distance between its components rather than the size of its components. The discovery. Remember when radio was all the rage in the entertainment world? Of course you don't. You're not 80 years old, but in the world of astronomy, radio is still important today, thanks to a discovery of Karl Jansky in 1931. His experiments with radio waves led him to find signals coming from the center of the galaxy, and he is considered the founding father of radio astronomy as a result of it. The fourth one is about the expanding universe. For thousands of years, astronomers wrestled with basic questions about the size and the age of the universe. Does the universe go on forever, or does it have an age somewhere? Has it always existed, or did it come to being sometime in the past? In 1929, Edwin Hubble, an astronomer at Caltech, was made a critical discovery that soon led to scientific answers for these questions. He discovered that the universe is expanding. The ancient Greeks recognized that it was difficult to imagine what an infinite universe might look like. But they also wondered that if the universe were finite and you stuck out your hand at the edge, where would your hand go? The Greeks' two problems with the universe represented a paradox. The universe had to be either finite or infinite, and both alternatives presented problems. After the rise of the modern astronomy, another paradox began to puzzle astronomers. In the early 80s, German astronomer Heinrich Olbers argued that the universe must be finite. If the universe were infinite and contained stars throughout, Olbers said, then if you look in any particular direction, your line of sight would eventually fall on the surface of a star. Although the apparent size of a star in the sky becomes smaller, and as the distance to the star increases, the brightness of its smaller surface remains constant. Therefore, if the universe were infinite, the whole surface of the night sky should be as bright as a star. Obviously, there are dark areas in the sky, so the universe must be finite. But when Isaac Newton discovered the law of gravity, he realized that gravity is always attractive. Every object in the universe attracts every other object. If the universe truly were finite, the attractive forces of all the objects in the universe should have caused the entire universe to collapse on itself. This clearly had not happened, and so astronomers were presented with a paradox. When Einstein developed his theory of gravity in the general theory of relativity, he thought he ran into the same problem that Newton did. His equation said that the universe should be either expanding or collapsing, yet he assumed that the universe was static. His original solution contained a constant term called the cosmological constant, which cancelled the effects of gravity on a very large scales and led to a static universe. After Hubble discovered that the universe was expanding, Einstein called the cosmological constant his greatest blunder. The discovery. Edwin Hubble gave the astronomy world a 1-2 punch or knowledge between 1924 and 1929. Not only was he the first to discover other galaxies, but by tracking their movement, he learned that they are moving away from us, and the ones farther away are moving faster, which was the first evidence we had to suggest that the universe is expanding. The fifth one is the theory of relativity. When the theory of relativity appeared in the early 19th century, it upended centuries of science and gave physicists a new understanding of space and time. Isaac Newton saw space and time as fixed, but in the new picture provided by special relativity and general relativity, they were fluid and malleable. Who came up with the theory relativity? Albert Einstein. He published the first part of his theory, special relativity, in the German physics journal Annalen der Physik in 1905 and completed his theory of general relativity only after another decade of difficult work. He presented the latter theory in a series of lectures in Berlin in late 1915 and published in the Annalen in 1916. The discovery. Albert Einstein, a German scientist you may have heard of, proposed his theory of relativity in 1915. Summed up, the theory states that mass can wrap both space and time, which allows large masses like stars to bend light. It's trippy stuff. The sixth one is the Herschel's map. Although Herschel's discovery of Uranus made his reputation, it was far from being his most important contribution. During the 18th century, astronomers had measured the proper motions of a reasonably large number of stars. Proper motion is the slow drift of a star with respect to its neighbors, which slowly causes the constellations to change shape. The first few proper motions were announced in 1718 by Halley, who found them by comparing recently observed star position with data recorded in Ptolemy's Almagest. Herschel noted that many of the stars with substantial proper motions are bright, which suggests that they might be nearby. He reasoned that if there is any pattern in the stellar proper motions, it might be due to the motion of the Sun through the field of stars. In 1783, Herschel published an analysis of 19 proper motions and concluded the Sun is traveling through space in the direction of the constellation Hercules toward a point called the solar apex. This was later questioned by the 19th century German astronomer and mathematician Friedrich Bessel, who had many more proper motions to work with, but Herschel's conclusion was ultimately proved correct. The discovery. From 1780 to 1834, telescope maker William Herschel and his sister Caroline systematically mapped the heavens, charting thousands of stars nebulae in the process. He also discovered Uranus, and if astronomers had stuck with his proposed name of Gorgium Sidus or Gorgeous George Star, we would have been saved by centuries of terrible jokes. The seventh one is the moons of Jupiter. There are 80 known moons of Jupiter, not counting a number of moonlets likely shed from the inner moons. Altogether, they form a satellite system which is called the Jovian system. The most massive of the moons are the four Galilean moons, Io, Europa, Ganymede, and Callisto, which were independently discovered in 1610 by Galileo Galilei and Simon Marius, and were the first object found to orbit a body that was neither Earth nor the Sun. Of Jupiter's moon, 8 are regular satellites with prograde and nearly circular orbits that are not greatly inclined with respect to Jupiter's equatorial plane. The Galilean satellites are nearly spherical in shape due to their planetary mass, and so would be considered at least dwarf planets if they were in direct orbit around the Sun. The other 4 regular satellites are much smaller and closer to Jupiter. This serves as sources of the dust that makes up Jupiter's rings. The, remain, the remainder of Jupiter's moons are irregular satellites whose prograde and retrograde orbits are much farther from Jupiter and have high inclinations and eccentricities. These moons were probably captured by Jupiter from solar orbits. 23 of the irregular satellites have not yet been officially named. The discovery. Galileo, arguably the most important scientist ever, used a fancy telescope he half invented and half stole the idea to discover 4 moons orbiting Jupiter in 1610. They were the first moons of another planet to be spotted, making them a landmark discovery. More importantly, we recently discovered that the moons of Jupiter would make a sweet band name. The 8th one is the Kepler's laws. Kepler's 3 laws describe how planetary bodies orbit the Sun. They describe how, number 1, planets move in elliptical orbits with the Sun as a focus. Number 2, a planet covers the same area of space in the same amount of time no matter where it is in its orbit. Number 3, a planet's orbital period is proportional to the size of its orbit, its semi-major axis. Kepler's first law. Each planet's orbit about the Sun is an ellipse. The Sun's center is always located at one focus of the orbital ellipse. The Sun is at one focus. The planet follows the ellipse in its orbit, meaning that the planet to Sun distance is constantly changing as the planet goes around its orbit. The Kepler's second law. The imaginary line rejoining a planet and the Sun sweeps equal areas of space during equal time intervals as the planet orbits. Basically, the planets do not move with constant speed along their orbits. Rather, their speed varies so that the line joining the center of the Sun and the planet sweeps out equal parts of an area in equal times. The point of nearest approach of the planet to the Sun is termed perihelion. The point of greatest separation is aphelion. Hence, by Kepler's second law, a planet is moving fastest when it is at perihelion and slowest at aphelion. The Kepler's third law. The squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axes of their orbits. Kepler's third law implies that the period for a planet to orbit the Sun increases rapidly with the radius of its orbit. Thus, we find the Mercury, the innermost planet, takes only 88 days to orbit the Sun. The Earth takes 365 days, while Saturn requires 10,759 days to do the same. Though Kepler had not known about gravitation when he came up with his 3 laws, they were instrumental in Isaac Newton deriving his theory of universal gravitation, which explained the unknown force behind Kepler's third law. Kepler and his theories were crucial in the better understanding of our solar system dynamics and as a springboard to newer theories that more accurately approximate our planetary orbits. The discovery. In 1609, German astronomer named Johannes Kepler told the world that planets move around the Sun on elliptical routes, not in perfect circles as was commonly believed. No, science can be boring when ellipses instead of circles is one of its most important discoveries. Number 9. The heliocentric model. The heliocentrism, also known as the heliocentric model, is the astronomical model in which the Earth and planets revolve around the Sun at the center of the universe. Historically, heliocentrism was opposed to the geocentrism, which placed the Earth at the center. The notion that the Earth revolves around the Sun had been proposed as early as the 3rd century BC by Aristarchus of Samos, who had been influenced by a concept presented by Philolaus of Croton. 470 to 385 BC. In the 5th century BC, the Greek philosophers Philolaus and Hesychus had the thought on different occasions that our Earth was spherical and revolving around a mystical central fire, and that this fire regulated the universe. In medieval Europe, however, Aristarchus' heliocentrism attracted little attention, possibly because scientific works of the Hellenistic period. It was not until the 16th century that a mathematical model of a heliocentric system was presented by the Renaissance mathematician, astronomer, and Catholic cleric Nicholas Copernicus, leading to the Copernican Revolution. In the following century, Johannes Kepler introduced elliptical orbits, and Galileo Galilei presented supporting observations made using a telescope. With the observation of William Herschel, Friedrich Bessel, and other astronomers, it was realized that the Sun, while near the barycenter of the solar system, was not at any center of the universe. The discovery. Astronomers had speculated about heliocentrism, the idea that the Earth revolves around the Sun, not the other way around, since ancient times, but in 1543, Copernicus was the first person to actually demonstrate the math behind the idea to prove it was a viable concept. The last one is the movement of the stars and planets. The motion in the sky. Observing and understanding motions in the sky is what led people to understand the layout of the solar system and to understand how the Earth moves in space. Objects can appear to move in the sky either because they are actually moving or because they reflect our motion through space. For stars, almost all apparent motion comes from reflex motion because they are so far away that their intrinsic motion appears very small. For planets, apparent motion in the sky comes from a combination of their intrinsic motion around the Sun and the reflex motion. The rotation of the Earth on its axis causes all objects to appear to move around the sky once each day. The apparent motion of a star to an observer which arises the Earth's rotation depends on the location of the observer on Earth and the location of the star relative to Earth's rotation axis. The discovery. Its stuff who wade through a couple thousand of years of ancient Babylonian, Egyptian, Greek, Indian, Chinese, Mayan, and Persian astronomical history to pick out the highlights. So I'm going to cheat and roll all of their achievements up into one entry. Maybe if their civilization hadn't died out, they would have got a better spot on this list. But because they couldn't keep their empires together, the ancient world gets stuck with the number 10 spot.